Hey, welcome back to Gaming for Tokens. I'm Marshall, and in this episode we're going to be talking a little bit about physics scripting. So doing some physics casts at runtime, that sort of thing. Should be pretty interesting, and it's kind of stepping into that more advanced scripting zone that I've been talking about getting into for a little while now. So hopefully you guys have been able to keep up so far, but I already have a blank scene here and in the same project directly that we've been looking at, so I still have my scripts that we've been seeing. So the first thing we're going to want to do is we're going to want to create a new script. And I'm going to call this, I don't know, forward ray detect. And that title will make sense in a second. So I'm going to go ahead and open this up in MonoDevelop. And go ahead and close my previous script in the previous video. And we're going to want to do a couple things here. Again, this is kind of stepping into the advanced scripting zone, so I'm going to type a bunch of stuff and then I'm going to explain what I'm saying. So we're going to say if physics.raycast, we're going to make a raycast hit called hit, and we're going to say transform.position plus offset, and we're going to make a new vector3 called offset that's going to equal vector3.forward, and that's going to be the origin, and then we're also going to have a MathF.infinity, and we're going to say transform.forward, let's see, what else do we need here? Float distance, layer mask, out hit. Alright, so I think I'm just about ready here. Out hit. So I'm going to make sure this doesn't have errors, which it doesn't. And fantastic. So what this does, this is using the physics class, just like in the last video we used the input class, so this is the physics class. Raycast is a function of that class, just like update and start is a function of the forward ray detect class. So we're calling a function. This function requires a couple different variables, and I was looking at these, if you noticed. I think I went with this option here. So you'll notice that this has a lot of options. This has a lot of different types of ways that we can do a raycast. And think about a raycast like, I'm going to look this direction that far away and see if there is something there. It's kind of it's an infinitesimally small I have such a hard time saying that word. So it's a tiny little beam of sight from a point in a direction with a distance. So if we tell it, hey, we want to look from this position that far away, is there something there, is essentially what it's going to be looking for. And it's going to be looking for colliders. So if the thing that we're looking for doesn't have a collider, then it won't ever find it. Anyway, so we're telling it to have an origin, a direction, and the raycast hit stuff I'll get to in a second. Well, I don't know. Basically, it's the raycast hit is an object that stores information related to our raycast. That's why it says out. We're outputting the data there. So if we hit something, then it's going to store the information of what we hit and how we hit there. I hope that makes sense. We might use it in this video, we might not. I don't know. We'll see. And then the float distance, so that's how far we're going to be looking. And that's the one I went with. There are others, like this one, which uses a layer mask. It's identical other than that. And there's this one, which uses a ray, which is a different type of construct that we can look at, maybe. I never really use them. But I prefer this one, or this one. I usually use this one, but I don't want to talk about layer masks today, because they're kind of complicated. But anyway, so physics raycast, and we feed it all these variables, all these random variables. So I know I never really talked about what vector 3s were. Vector 3 is positional information. So if you're familiar, if you've taken any algebra classes, I believe I took in high school algebra, we talked about vectors, but not with that name. So a vector is an x, a y, and a z coordinate. So if we wanted, this is essentially what a vector 3 looks like, is this right here. If we wanted to say, by the way, this vector 3 is actually going to be at this position. Notice how there are 3 values up here and there are 3 values in the vector 3. That's because this is a vector 3. Don't confuse that with rotation. The rotation here is not a vector 3. That's a quaternion, and that's complicated. But this right here is the vector 3 of 0, 0, 0. If we wanted this to be 1, then we could change that to be 1, and now those are the same again. Vector 3s, they're not that complicated, but they can get complicated if you do some advanced things with them. But there are also default vector 3s, like the vector 3.forward. I believe there's more than that to... Jeez. Alright, so there's forward, there's up, I believe. Yeah, there's dot right. I don't know if there's a left. There's a left, there's a down, there's all sorts of default vectors. But vector 3.forward is going to be 1 point forward on the z-axis. So what this is going to equal is 0, 0, 1. Ooh, I keep hitting wrong keys. There we go. 0, 0, 1 is what this is going to be. There's a reason why I did that, and I'll explain that in a second. But just know that that's what I did there. Transform.position. A transform object is it's basically this. It's what this is up here. So a transform is the thing that stores positional, rotational, and scale value information. So every game object usually has one, and you can remove them, I think. No, you can't remove them, because everything has to have a transform if it's a game object. That makes sense. So transform.position is that value right there. That is the positional value that I'm getting. And I'm adding the offset. So this is, as the name says, this is an offset. So essentially what this is going to get is the position of my game object plus 1 on the z-axis. So it's going to get 1 unit in front of my object. And then transform.forward is the direction that the object is facing. That's essentially, if we're looking at local up here on the top, that's going to be the direction that our z, our blue arrow is pointing. So if we rotate this object, now it's over there. That's our forward axis. And if we rotate it this way and then down, then now that's our forward axis, because that's where our object is facing. That's kind of important with what we'll be doing. I don't think we'll be doing much rotation, but you'll see why that's important in a minute, because that's the direction that we're casting in. And then we're going to output our data to the hit variable, which I created up here. And we're going to go, this is our distance, we're going to cast to infinity. Now, infinity is a really it can be a really dangerous thing to use. In this particular instance, it's not. And how you access it is by MathF, which is, it's another class that lets you do math functions. So, for example, mathf.round or mathf.pow to get a power of something, or repeat, or round to, I already talked about sine, smooth dampening, all sorts of square rooting, stuff like that. It's essentially your calculator in Unity, like a sine, ceiling, and clamp. So you can do all sorts of fancy math functions with it. It's really, really great for for if you're dealing with a lot of numbers in order to get the numbers you need, or the types of numbers that you need. It's essentially your I want a number function, or your I want a number class. And infinity is a variable on it that is infinity. So we want to go infinitely in, we want to raycast infinitely on the forward axis of our object from this position of our object. Now, if you notice, this whole thing is wrapped in an if statement, because physics.raycast returns a boolean, true or false. It returns true if we hit something, and false if we did not hit something. So by wrapping this in an if statement, what I'm saying is, if we hit something with these variables, then do this stuff down here. this is usually how all of my raycast stuff looks, and with the exception of no layer mask, because I don't want to talk about layer masks right now. The this is pretty useful in for this is what you'll be using a lot of the time. So to see this, what we're going to say is we're going to say debug.drawLine or draw ray, I guess. Yeah, we can draw a ray. Okay, so we're going to do draw ray. So draw ray takes a couple variables, and I think we're going to use this set, the number 2 of 4. And we're going to feed it the same start position we did the ray here, and we're going to feed it transform dot forward. But notice how this isn't taking any information for depth in. It's not taking the distance that we're casting. It's just taking the direction and the position, because the distance by default on the draw ray debug function is 1. So it's just assuming that we want to just check for 1. If we don't want to check for 1, then what we can do is we can multiply the direction by the distance that we want to use. So if we yeah, I hope that kind of makes sense. It's kind of strange, but this right here, as far as the debug draw line is concerned, is the exact same thing as this up here. And now next thing we can do is feed it a color, which is just color dot whatever color we want. So I'm going to do a cyan color because I like cyan for whatever reason. And so now when we start this, I want to delete this, and I want to say create a new cube. I'm going to go ahead and drop my forward ray detect on it. And what we're going to see here when I start it is nothing. That strikes me as odd. Oh, we want this to be public. Debug.drawRay. I wonder why it's not. Well, maybe if we don't multiply this by infinity. Sorry, I'm kind of at a loss here for why that's not working. Okay, so yeah, now we're getting our raycast there. Apparently infinity doesn't work for draw line. That's bizarre. Anyway, so you'll notice that being our cube is 1 wide, half of that cube, because we're reading from the center position, is 0.5. So another 0.5 out from that is where we're starting our raycast, right? So all the way out here. And again, because of the draw line thing, we're only going out 1 unit. So if instead we wanted to say public float distance, we're going to say that's going to be equal to 999f. Then we can say instead of MathF.infinity, we can just use dist. And instead of this, we can say times dist. And now in theory, we should actually get what we... Yeah, there we go. So now we're going to go 999 units out from the front of our object. That is our raycast line, and if we wanted to change our offset so that it actually met the front of our cube, which is what I was trying to do there, we would change this from 1 to 0.5. So now we're starting at the middle section of the front of our cube, and we're casting out 999 units in front of it. And because we were running, we want to change that back to 0.5 now. The reason why I wanted an offset, I wanted to not start at the center position of this cube, is because this cube happens to have a collider. And I believe physics detection will read whenever it passes through the wall of a collider. So being that this is a wall of a collider, and if we are inside and casting out of it, it will read that as detection. Sometimes that's the case, sometimes that's not the case. I know that it used to be the case, and maybe it's just old practice of mine to not do that, but if you want to get solid numbers, you should never collide with yourself. That's usually what layer masks are for. Again, don't want to talk about those right now, but you can use an offset vector as a way of getting around that. So this right here is detecting a thing. So if we hit, I want to cast a cyan. No, wait. If we don't hit, I want to cast a cyan thing. If we do hit, I want to cast a red line. And I don't want to cast it to the distance that we're actually going to. What I want to do is, okay. So if we're hitting something, then I want to cast to the position that we're hitting rather than to the distance that we're looking, if that makes sense at all. If we're hitting something, I want to cast a line from where we're casting from to the point in which we hit. And in order to do that, I need to say times vector, not 2, 3, dot distance. And that'll give me, I give it two vector 3s, so I give it a start and a direction. Wait, this is, what? That's not what I wanted at all. There we go. So you give it you give it an A and a B location, and the A location is where you're coming, is the first one and the second one. So it doesn't really matter what order you put them in. But basically what I want to say is I want to say transform dot position and hit dot point. So what we're saying here is that like we were doing before, the distance that we're casting, but instead of the distance that we're casting, we want to go to the location that we hit. And in order to do that, we're going to say forward, because we're casting forward, and we're going to multiply that by whatever the distance between our position and the position that we hit, being we're casting from our position. But we're not actually casting from our position because we have to add the offset value. I almost forgot that. So now, when we do this, if we hit an object, we will cast to that object. Let me go ahead and save this. And so right now we're not hitting anything. But if I add another cube, and I move that cube in front, see how it changes red and the line cuts off? It's kind of like a laser. So if I rotate this object, the line will actually fit to the object. Just like if I rotate and move around this object. See how it's reading that we're hitting that object because we are. And also it is extending the line that we are hitting with to the value in which, to the distance and point that we are hitting in. So if I move it along that sloped surface there, it'll actually match up to it. This is a really, really decent way to do things like lasers in games, or you'll be seeing this is a really, really great way to do projectiles in games, like bullets and things like that. Because we want to know if we hit something, but we want to know if, I don't know, we want to know if we hit something, but we want to know, yeah, we want to know if we hit something. That's basically the point that I'm trying to get across. Anyway. So this is raycast. There's a couple other types of physics stuff, like the one that we're going to be using for a projectile specifically is physics.linecast, and that's where we feed it. Again, this only has 4 instead of 12, but the one that I usually use is this one, the 4th one, the most advanced. We have a start position and end position, so it's going to draw a line from a location to another location. It's going to feed any output information, just like we did before, to the raycast hit, and it's also going to use a layer mask. And I'll be talking about layer masks in our next video, I think, because they're kind of important for this, but they're kind of complicated too. So just like raycast, it's going to simulate a bead of physics from a point to a point. In this particular case, it doesn't have an endpoint. That's the difference between raycast and linecast, is that ray doesn't have an end. It just has a direction, and it just goes, and however far you want it to go. And then linecast says, okay, go from here to there. So linecast is really, really great if you want, like, say you have a like a Tesla coil kind of thing, where you have 2 spheres and you want to detect if anything ever gets between those 2 spheres. Then you can say, great, linecast between the 2. If there's anything that it hits, then do a thing. The other thing that there is a physics.spherecast. Ooh, there we go, spherecast, which is effectively the same kind of thing. This one has 9 different things that you can use, 9 different types of things that you can send it. And this one has an origin, which is the point that you start at, and it has a radius, so just like a sphere would have, and a direction, kind of like the raycast does. And it also has the output and the distance that you go. So it's basically a raycast with, I don't know that it actually has a linecast option. It might. I've never really looked. I have used this before, but yeah, okay, so it doesn't. So it's just like raycast, except it uses a volume instead. So it has a radius. Think about it like, instead of a cube, we have a sphere, and instead of, so it'll look like this when it's casting, right? It's checking each point with a certain radius of a sphere at each point. And but think about this more like if it's a capsule. So it checks it like it's a capsule. It's really, really useful for, I find, for things like should this object be able to fit through this hole or things like that. Because if you use a raycast is infinitesimally small, right? So it can fit through the hole. So if you use that kind of a check, then it'll just know that it can. But if you use a sphere cast, then it can actually detect a volume better than it can a ray. There's also because Linecast and raycast are infinitesimally small. Physics cast is the only thing, or sphere cast is the only thing that can actually like read a volume. As far as I know, that isn't like just the pure physics detection. Which, by the way, this is all the raycasting stuff that you can do. There's also just like start and update. There's other monobehavior functions that you can access by typing void on collision enter. So this is a function that's going to fire when the collider of this object meets the collider of another object. This is when the frame that they touch, and there's also a counterpart to it on collision exit. So this is when the two objects stop touching. The kind of like the last video that I talked about with inputs, there's the on button up, on button down. This is on collision enter, this is on collision exit. There was also the on button. There's also void on collision stay. So again, on collision enter should fire once, on collision exit should fire once, on collision stay is going to be that intermediate state that fires every frame that that this object is touching another object. So when this object starts touching another object, when this object stops touching another object is on collision exit, and when this object is touching another object is on collision stay. So again, you only want to use on collision stay if you want to detect how long something is touching something else, basically, or every frame that something is touching something else. Usually what you want to do is you usually want to run on enter or on exit. I've only used on stay a couple times, and it's usually good for things like, I don't know, in a flight sim, if you're grinding against a wall, you might want to use on collision stay. You want to know that you're hitting it and you want to damage the ship, that kind of thing. Otherwise, you want to use on collision enter for like if you run into a wall and bounce off of it. That's really great. Or a good example is like sticking with the flight sim example. So if you hit a wall, you want to do a lot of damage when you hit it and less damage when you're grinding against it. Do a lot of damage here and a little damage here, if that makes sense. And then on collision exit, it doesn't really matter. It's just, you wouldn't use it in that example. But it's kind of useful for some things. There's also on, void on trigger enter, which this is kind of getting a little weird, but the every collider has an is trigger checkbox, and triggers are separate from they're colliders that you don't actually hit. So the easiest way that I can think to explain how they work, if you don't know anything about physics simulation stuff in games, is a lot of time checkpoints will be triggers. They're things that I I want to detect when this object hits that object, but I don't want you to actually hit this object. So if we removed this renderer, if we made this not render anything and it was just a cube with a box collider, if it's just a box collider, then this should be a trigger, and this means that hypothetically in a game that is relatively finished, you could have your player object walk through this object and have something happen when the trigger is hit. So on a lot of games you end up with some cinematic stuff like you walk into a room and a wall explodes or something like that. The thing that triggered the wall explosion was you walking into a trigger volume, if that makes sense at all. And again, these don't necessarily have to be box colliders. They can be anything you want them to be. They can be, we'll slap a physics collider on it, we'll remove the box collider, and we'll say that this is a trigger. Now this is a trigger volume that's not a box. And every single, I believe, except for mesh colliders, every collider, if you hold down shift, you get the opportunity to edit the objects, or the object attributes, like the size of it and all that stuff. So if you add the box collider back onto this, you remove the sphere collider again, we make that a trigger, we can actually resize this thing by holding down the shift and clicking the little boxes on the object. So this is sometimes really useful, especially for if you are making like a checkpoint volume or something like that, and you need to like fit the object arbitrarily to the space that is the level. You can kind of get away with it with this. And you can add multiple of the same thing. It's not a good idea, but you can. So I believe if all of these are set to trigger, then you can detect, like, this could be a checkpoint where there's like, I don't know. The point is, like, this is all one big trigger now for this script, because either one of these colliders will fire the on trigger enter script. So, and again, just like before, there's on trigger exit, on trigger stay. There's all sorts of stuff like that. These are fantastic for things, like I said, like checkpoints or like walls or things like that. For projectiles, I'm a firm believer that you want to use raycasts and linecasts and things like that. It's a lot cheaper because, again, you never know how many projectiles you're going to have on screen. So you could have, you know, if everybody has, like in Counter-Strike, for example, if everybody has AK-47s, you could have somewhere around, like, I don't know, 75 to 100 bullets on screen in the game at once. And if that's the case, that means that you're doing a lot of physics simulation for stuff you don't need to have physically simulated. On top of the fact that this is, I think, the major reason why. So pretend that we have a wall. I think I talked about this in a previous video a little bit, but hypothetically we have a wall, and well, not hypothetically, I guess it is a wall, and we have a cube, and we wanted to, this is our bullet and this is our wall. We want to detect when this bullet hits this wall, and it's moving so quickly that first frame it's here, second frame it's here. So it never actually hit the wall. It was here and now it's here, because that's how movement in games works. It's not like it's every single frame stuff is in a new position, and that simulates movement. So if something is here and then it is here, it never actually hit the wall. The only time that on collision enter would trigger is if it was in this kind of a state when a new frame happened. So you might be asking yourself, well, that makes on collision enter really crappy. Well, not really. I mean, it still has a purpose. Like I said, for character movement and for walls and things like that, it's fantastic. For things that are slow moving and things that aren't going to jump through things, as long as like, I don't know, it depends on the speed of the object, I guess, is what I'm trying to get at. Is if something is moving really quickly and it's going to potentially phase through things because of how fast it's going, then yes, you're going to want to use raycasts instead of physics, or sphere casts if it has some sort of volume. The only thing I can think of with that is, like, a rocket would be better with a sphere cast than it would be with a raycast, because a rocket can be kind of bigger, or a rock, a boulder, that kind of thing. But a bullet, for example, is usually pretty tiny, so you can get away with a line cast or a raycast. because the linecast and raycast, what you can do is you can check every frame against the position that it was in. So if an object is here and then it went to here, you can do a linecast from here to there and say, oh, there's an object between, we probably should go back to here. And now we can run all of our physics simulation stuff. Great, perfect. And that's kind of what I'm going to walk you guys through in the next video. But just know that that's a thing that can happen. And these are what I covered in the scripting was the kind of ways that you can read when an object hits something and when an object hasn't hit something. And these draw rays are fantastic. Draw lines are even more fantastic for debugging information with physics. So hopefully that was a little helpful. And just again to walk you guys through, I'm going to put my forward ray detect on this cube and I'm going to play. And so because we're looking off that way, we don't actually see anything, but if we rotate this guy around, as soon as we look at that thing, we hit now. And again, it's simulating from 0 here. So if we, from 1 there, so if we make that 0, in this particular instance, the raycast is not detecting on the inside of the cube, but sometimes it will, sometimes it won't. So be prepared for that if that happens. But yeah, that is physics casting and simulation for the most part, having to do with scripting and I mean that's the basics. That should get us where we need to be to start making a thing. So next video we're gonna start talking about projectiles and guns and getting a first-person shooter up and running. So hopefully this was helpful, and I really like physics scripting. It's hard for me to describe how some of it works because a lot of it I've just kind of haphazardly come across, but yeah, I think that's everything. So look forward to the next video, and bye-bye.